Good afternoon. Welcome to our lesson on reaction mechanisms and catalysis, in which we'll learn how reactions proceed, how the reaction mechanism is connected to the rate law, and how catalysts work. First, what is a reaction mechanism? Reaction mechanism is merely the sequence of elementary steps, in which an elementary step is usually two or fewer reactants coming together in a simple reaction, such as seen down below here, in which the steps represent progress towards and add up to an overall reaction. So for example, I've got this reaction of 2 NO gas plus 2 hydrogen gas producing nitrogen gas and 2 water molecules. And the proposed mechanism says that in the first step, 2 NO molecules will react to form N2O2, and that will be a fast step. And then the N2O2 will react with one of the hydrogen molecules to produce N2O gas and one of the H2O gas molecule products. And this is going to be slow step, which we're going to introduce as the rate determining step. And finally, the N2O that was produced in the second reaction will react with the second hydrogen gas to produce nitrogen gas and the second water molecule. The diagram, the energy diagram that describes this reaction is seen down below. And in this reaction mechanism you see, or in this diagram, you see that there is one activation energy for each of the elementary steps. So we have an EA1, an EA2, and an EA3. EA1 here, EA2, activation energy 2, and activation energy 3. And at the top of each one of these, there's an activated complex, a different activated complex for each one of these mechanisms, for each one of these steps. The largest of the activation energies, the second step in this case, is going to give us the slowest or rate determining step. This is because it takes more energy for the reactants to get to the top of this activated complex, and so it's going to have the slowest K, the slowest rate constant of all of these reactions, and so it's going to be the one that slows things down. There are intermediates at each trough. So the intermediates in this case are going to be the N2O2 that's produced in the first reaction and the N2O that's produced in the second reaction. So the N2O2 and the N2O are the intermediates, and definition for an intermediate is that it is a species that is produced in one step and it's then subsequently consumed in a subsequent step, but does not appear in the overall reaction. Now, in these reactions, in each of these reaction mechanisms, each step is represented by a molecularity, where the molecularity is the number of particles colliding at the same time in an elementary step. The rate law depends on the molecularity of the rate determining step. So for example, if we have molecule A colliding with molecule B, it would be a bimolecular reaction. Two molecules coming together to form the product, or at least the product of that elementary step. So if we assume that molecule A collides with molecule B in the rate determining step, then we're going to see that the rate determining step should be A plus B giving C. And it should make sense that from this step that the rate law should be that we're proportional to the concentration of A times the concentration of B. Now this is going to be because, as we saw in yesterday's lesson, that the number of collisions is proportional to the concentration. So as you double A or as you double B, the rate should increase and the rate should double. If we end up having two molecules of A that need to collide in order to react with each other, then we would have this situation very similar to what you see up above, except the B would be replaced by a second A. So in this case, the rate law is going to end up being 2A going to C, or The rate is K times A or Ka squared, and this is one way in which we would get a second order reaction. So there are a number of different ways to get to the different molecularities, and what everything is going to come out to indicate is that the coefficients in the rate determining step, this is always going to be for the rate determining step, are going to indicate the exponents in the rate law. So we can have a unimolecular reaction where one reactant is present, and this is going to give us a first order overall and first order in A reaction. If we have two reactants coming together, this is a bimolecular reaction. These are by far the most common because usually we have two reactants coming together in the rate determining step. And as we saw on the previous page, we can either have two A's coming together, in which case we have a second order in A and second order overall, or we can have an A and a B coming together, in which case we'll have a mechanism that's first order in A, first order in B, and second order overall. Slightly rarer than that is a termolecular reaction that gives us a tertiary or third order reaction. For these, there are three ways of getting it: either three A's coming together, two A's and a B, or three different reactants coming together. These are relatively rare because the probability of having three particles colliding in the correct orientation and with sufficient kinetic energy is relatively low. And we'll see as we go through this lesson that there are other ways to get to a third order overall reaction, such as you see in the K times A squared times B. The typical kind of question that you would get for this, let me get rid of those, would give you several possible mechanisms for an overall reaction and either give you the rate law, as I've done here. Here's the rate law for this reaction, or it could also tell you, we give you a specific mechanism, one mechanism, and ask you to determine what the rate law would be. And so what you have to go through is you have to take a look at the various mechanisms and try to determine which one of them matches or can give us that particular rate law. So for example, reaction mechanism number 1 has NO squared, because there's two NOs, times the concentration of F2 would be the rate determining step, and that does not match because we don't have two NO2s, sorry about that, two NO2s. In the second reaction, so we have a slow step as our second step, and that tells us that we would have NO2 and F as our rate determining step. And since we don't have a reaction that has F as one of the reactants in the rate law, this doesn't match. And in the third step, in the third possible reaction, we have unimolecular in NO2, unimolecular in F2, and so this particular mechanism does match. This particular third mechanism does match the rate law. Note that the mechanism that we get must always add up to the overall reaction. In these three mechanisms, they do add up to the overall reaction. Be aware, be careful. Sometimes you will be given mechanisms that don't add up to the overall reaction, and you have to be careful to weed those out from the possible consistent reaction mechanisms. So, how do we go from the reaction mechanism to the rate law? So, there are two different possibilities. One is that we have a mechanism with a slow initial step. if the first step is a slow rate determining step, then the rate law depends only on that step. For example, NO2 and carbon monoxide coming together to form NO and carbon dioxide. This is the mechanism that's proposed, in which in the first step we have two NO2s needing to collide together to form NO3 and NO. And those NO3s and NOs are going to be, well, the NO is one of the products, but the NO3 now is going to be an intermediate, and then that NO3 would subsequently collide very fast and very quickly with the carbon monoxide. So the second step happens quickly. As soon as an NO3 is produced, then it reacts with the CO to produce the products, and that would be a fast mechanism. So since the second step is much faster, the first step is rate determining. K2, the rate constant for the second reaction, is much larger than K1, and so the rate law is going to equal K1 times NO2 squared, because NO2, we're bimolecular NO2, and we're just going to convert that K1 to the overall rate constant for the reaction, and we get our rate law of K times NO2 squared. So again, overall the reaction is going to match the molecularity of the rate determining step. Now, competing mechanisms may exist, but the fastest route does dominate. Also notice that this reaction would be zero order in carbon monoxide. The reason that it's zero order in carbon monoxide is that the carbon monoxide comes into the reaction after the rate determining step. So anything that has a reactant that you need but is zero order, that reactant must come in after the rate determining step. If we have an initial fast step and a subsequent slow step, then we have a little extra stuff that we have to work on. So if we have this reaction with a proposed rate law, an observed rate law, that's bimolecular in NO and unimolecular in Br2, so second order in NO, first order in Br2. It's unlikely that this is going to occur in a single termomolecular step, and so the following mechanism, by the way, this would have to be confirmed spectroscopically or some other method of confirming that these intermediates exist. The intermediates are not able to be collected, but they can be observed spectroscopically. So in this step, we first have a fast equilibrium in which this reaction in the forward direction and the reverse direction happens quickly, and that reaction is continuing, and every once in a while then one of those intermediate NOBr2s will react with the NO in the slow rate determining step to form the two NOBr products. So as I said, reaction 1 then is a reversible fast equilibrium, and K1 and K negative 1, the reverse rate constant for that reaction, are much, much larger than K2. The rate law would, if you look at the reaction, have the NOBr2 and the NO both first order, but NOBr2 is an intermediate, and we really don't have any way of knowing the concentration of this or controlling the concentration of this. So what we're going to do is go back to our first reaction and say, all right, we know that in equilibrium, the rate of the forward reaction, which is K1 times NO, concentration NO times the concentration of Br2, must be equal to the rate of the reverse reaction, which is K negative 1 times the concentration of the NOBr2. And rearranging that, we get that the concentration of the NOBr2 can be expressed in terms of the forward and reverse rate constant and the concentrations of the initial reactants. So now what we're going to do is take that and substitute into the rate law for the concentration of the NOBr2, and that's going to give us this expression down below. We're going to rearrange some things now. We're going to notice that the K's are all constant, so we can combine them into one overall rate constant, and we're going to combine terms and combine the two NO concentrations into an NO squared. And because we've done this, we now have the reaction mechanism that we saw before, that we have K times NO squared times Br2, so it's an overall third order reaction. We have the combined rate constant here. Doesn't matter how we got to there, the fact that we have three constants coming together to form a single constant should be fine. And in this case, it's purely coincidental that this rate corresponds to the reaction stoichiometry. That is not always going to happen. In fact, don't necessarily look for that to happen. So how do catalysts fit into all this? A catalyst is a substance that changes the rate of the reaction, a little low there, without undergoing a permanent change itself. So in other words, we're going to have to get the catalyst back. Now, I am going to post along with this video links to two YouTube videos on catalyst demos that I like to do. Some of you have seen them before. Please go ahead and look at those catalyst videos. One of them is really good at showing that this permanent change doesn't happen, that it does come back in the original form. The way catalyst works is by generally changing the reaction mechanism, providing, as we call, an alternate pathway, which lowers the activation energy. Now, there's a little math here I'm going to throw at you. You're not responsible for this, but I just wanted to show you that if we take the ratio of the catalyzed rate constant to the uncatalyzed rate constant, what's going to end up happening is that we're going to have in our exponent here now here's an exponent. I just realized I haven't thrown this particular equation at you. Oh, yes, I did. Sorry, this is from the Arrhenius equation yesterday. Sorry, I'm getting confused as to my two different lessons. The Arrhenius equation, now the exponent is going to be reduced because the catalyzed catalyzed activation energy is smaller than the uncatalyzed activation energy. So in this case, the exponential term is going to be less negative, and so the ratio is going to be a positive, or is going to be a number that's greater than 1. And so we've got a catalyzed rate constant which is greater than the 1, and the catalyzed rate constant is going to be greater than the uncatalyzed rate constant. Again, don't worry too much about that. I just wanted to show you how that worked. Two main types of catalysts we've got. We've got homogeneous catalyst and a heterogeneous catalyst, and let's look at how those two catalysts work. First, a homogeneous catalyst is present in the same phase as the reactants. This particular catalyst kind of catalyst is what you're going to see in the two videos that I've posted. So homogeneous catalyst present in the same phase as those reactants. So this is the decomposition of H2O2. This is the elephant toothpaste demo. The decomposition of H2O2 into H2O plus H2O. And plus O2, sorry. And relatively high activation energy, 75 kilojoules per mole. If we add iodide, in this case potassium iodide, I think in the video they used sodium iodide, but it's the iodide that's important. It reduces the activation energy to 56.5 kilojoules per mole with a two-step mechanism. So here is the catalyzed reaction mechanism. The first step is the rate determining step, as you can see, because the activation energy is higher. Not sure what the activation energy is here, but it's got to be less than 56.5 kilojoules per mole. And so in our first mechanism, in our first step, the iodide comes in and catalyzes the H2O2, catalyzes the reduction of the H2O2 to H2O, and this intermediate, IO minus, then subsequently the IO minus gets consumed in the next step. H2O2 plus the IO minus gives us IO2 and H2O, and then look at this, the I minus is coming back out as the catalyst. again, the catalyst must come out in a subsequent step. So the catalyst is always going to go in the rate determining step. So always look for that catalyst in the rate determining step. It makes sense that it must be the rate determining step, because if you didn't have the catalyst in the rate determining step, it would have no effect on the speed of the reaction. All right, and the IO is the intermediate, and the IO minus would presumably be right up here in the trough. Heterogeneous catalysis takes place in which a catalyst is in a different phase. This is usually a solid catalyst that's in like an aqueous solution or a gas phase reaction. And one example is the catalysis of the hydrogenation of ethyne, C2H4, on a metal. And so we have this mechanism in which the H2 and the C2H4 adsorb onto the surface of the metal, and the H's break apart, and one of the H's then comes over and reacts with the C2H4, and then the second H atom comes over and reacts with the C2H5, and finally the molecule, the ethane, finally desorbs from the surface, and this is the activation energy. This is the reaction pathway that would show this particular reaction. And the adsorbing, interesting that the adsorbed reactants have a lower energy than they had to begin with, so slightly exothermic there. And then on the surface we have a reaction activation energy which is smaller than in the gas phase, and then the adsorbed products come off in the very end and give us our gas phase products. Finally, special catalysts. A special catalyst is an enzyme, a biological catalyst that decreases the activation energy and at the same time increases that frequency factor A that we saw yesterday in the Arrhenius equation. So this is the only kind of catalyst that actually affects that A value. Everything else all catalysts only affect the activation energy. So there we have this particular mechanism in which we have two substrates which have to come together. S is the substrate, so substrate 1, substrate 2 has to come together on the enzyme. The enzyme then locks the two substrates together into their preferred orientation, lowers the activation energy, and gets them locked into the correct orientation before we get to our product. We can have an inhibition. An inhibitor reduces the reaction rate by either increasing the activation energy or by reducing that frequency factor. And two kinds of inhibition. I'm not sure that this is going to be relatively important, but it's interesting to see. A competitive inhibition in which I, the inhibitor, now fits into the chemical key on the enzyme, locks in preferentially and keeps the substrate from coming in, so is unable to react. The other thing that an inhibitor can do, an inhibitor can come in on some other side, some other place on the enzyme, and when it does that, it changes the chemistry at the active site for the catalysis, and then that substrate can no longer lock in. All right, so that's our look at rate mechanisms and catalysis. Please download the notes if you need to. They will have everything that you saw on here that you need to see for working on the homework. Please help each other out. Have a good rest of the day, and I will see you tomorrow.